Well, hello. Today we are going to be looking at light and some of the characteristics of light. Hopefully this will shed some light on the subject. A couple things you want to know, just so we clean up our language here. When I use the word light, I am referring to all forms of electromagnetic radiation, all electromagnetic waves. Some people refer to light as that which you can see with your eyes. And then they use the term electromagnetic waves or radiation as the big group. I use light as everything, and then I use the word visible light to mean that which we can see with your eyes. Different people will use the words slightly differently, and that's okay as long as you understand what we're using it as. So I will use visible light as a subset of light. Okay, first off, another thing you want to know is light is a transverse wave. It's not longitudinal like sound. It is a transverse wave. Okay, and some other terms that we're going to want to know is having to do with luminous and illuminated. Okay, so luminous means it's giving off light. A light bulb is luminous when you have it. The sun is luminous. Things that receive light are illuminated. So chances are you are illuminated by a light, or the moon is illuminated by the sun. Okay. Now, transparent, translucent, and opaque. When you can see through something clearly, like a window, it's transparent. When light can go through, but you can't see through it clearly, like a lampshade or a frosted window, that would be translucent. And something that light doesn't travel through at all is opaque. Now, I'm going to try to change some of our understanding of this, because all these terms are dependent upon which part of the spectrum you're in. And we're going to kind of see that as you go, because something may be, for example, you are illuminated in the visible spectrum, but you are actually glowing. You are luminous in the infrared spectrum. And so you might think of something as luminous or illuminated. Well, it depends on what part of the spectrum you're in. Likewise, you might think of walls of your house as being opaque. Light can't get through them. Well, radio waves can get through them, and therefore they would be at least translucent, if not transparent, when it comes to radio waves. So we have these terms. These are good terms to know, but how you classify something is really dependent upon what part of the spectrum you're in. Okay, so now what we want to know here in terms of the spectrum is you don't need to memorize all these numbers, but what you do want to be able to do is know the relative order of these things when it comes to, and we're going to go through each one of these. So the relative order, and what you want to know is frequency, wavelength, and energy. What's high and low. You just need to know that's one of the things you're going to be tested on, is what is a high energy wave as opposed to a low energy wave. What are small wavelengths? What are small frequencies? So the relative order is on the left-hand side. We have, radio waves. They are very large wavelengths. They are the largest of the wavelengths. They are the lowest energy. They have the lowest frequency. Microwaves would be a little bit smaller waves, higher frequency. Then there's infrared, visible. In the visible spectrum, we would break that up into the colors, Roy G. Biv. And then ultraviolet, X-ray, and gamma. So you should know that relative order. Now, they all travel at the same speed. And so this is something you want to memorize in terms of the speed. And that would be the speed of light. We give it the letter C, and that is 3 times 10 to the 8th meters per second. It's actually 2.99 and some change. But if you just use it as 3 times 10 to the 8th meters per second, and that's in a vacuum, empty space. See, light can travel through empty space where sound cannot. Light is a disturbance in the electric and magnetic fields, and you don't have to have a material substance in order for that field to exist. And so light can travel through empty space, but sound cannot. Therefore, we can see the sun because it gives off light, but we never hear the sun. We don't wake up in the morning and say, oh, the sun is really loud today. We assume the sun is really loud, but there's no medium between us and the sun, so we don't hear it. But we don't have a medium, but we can see it. Light can travel through empty space. So that's one of the strange things about light. Many scientists in the early 1900s spent a lot of time trying to figure out what is the medium of light. Light has wave-type properties, and every wave we can think of has a medium. And they searched for it, and they gave it a name, but they couldn't find it. They referred to it as the ether. Okay. Now, the speed of light, although light does not need a medium per se, whatever it's in does affect its speed slightly. So we do say the speed of light in a vacuum is 3 times 10 to the 8th meters per second. It slows down a little bit when it gets into the air, but when we do calculations, when you're using air, you can just use 3 times 10 to the 8th meters per second. But when it goes into, say, a piece of glass, then it might slow down to something closer to 2 times 10 to the 8th meters per second. We'll get into those situations a little bit more as we move along. Okay, but one thing you just want to memorize, 3 times 10 to the 8th meters per second. That's worth the price of admission. If you will just simply get that memorized, that will be helpful. Okay. Now, we classify the different forms of light, just like we classify sounds by frequency and wavelength, and we might classify them and say this is a note, certain particular note. Well, we do that with light, and we actually can subdivide these even further. You can look at the near infrared and the far infrared, and we can talk about soft X-rays and hard X-rays. And so each of these classifications I'm giving you can be broken down even farther. Just like the visible light can be broken down into different colors, we can break down each of these classifications. Okay, the visible spectrum, the part that you are used to, is a very small portion of the entire spectrum. We as humans, our eyes, we miss most of what there is to be seen. Okay, there's just we see very little. So let's go on. Let's talk a little bit about each of these. Once again, what I think you should really focus on is not memorizing all these numbers at the top, but to keep an idea that what's big and what's small and the relative order. So the biggest of the waves, radio waves. We have communication. That's the big thing. You may listen to radio stations, AM and FM. Well, what does AM and FM stand for? Well, the M stands for modulation or modulate, and that simply means to change. So when you have a wave, we refer to the wave as carrying information. So we talk about a wave carrier. And we encode waves with information, but you have to change it. So for example, I could whistle, and that's a wave, and it has information. But there's not much information in there because it's the same thing over and over and over and over. But if I modulate the frequency, I can send you a message because you've got this information encoded in there. So just by using a familiar tune, modulating in such a way that you are familiar with it, I could send you that information and make you think thoughts about happy birthday because I encoded that information. Well, in radio stations, they can encode information into a form of light waves. Radio waves are actually a form of light. They're not a form of sound. They travel at the speed of light, but they carry information, and they can either it can either be encoded by modulating or changing the amplitude, AM, or by modulating or changing the frequency, which is FM. FM is typically used for your multiple signals, stereo as such, and AM more of your talk radio. At least that's the way it used to be. Not as much anymore, but still can be that way. And so by encoding information into the wave carrier. They send it to your radio, your receiver decodes that information and then turns it into a sound wave. But the radio waves themselves are actually a form of light. Moving on to some smaller waves, we have microwaves, and they're from about 30 centimeters to about 1 millimeter. They're also used in communication for radar. But in your house, you have a microwave source, and that is for cooking. And why are microwaves used for cooking? Well, you have to think of molecules as little instruments that can vibrate, like little springs. They can vibrate at certain frequencies. And one of the natural frequencies of one of the most common molecules in almost all of your food is in the microwave range, and that molecule is water. And so water will, like an instrument, can resonate at multiple frequencies. One of those frequencies is in that microwave range, and so your microwave ovens are tuned so that they will heat up water molecules. And so one of the things you can do to show this, like for example, you could take at home, you could take two microwave safe containers, stick water in both of them, but freeze one of them. So one of them's cold, a chunk of ice, and the other one's got water. Stick them both in the microwave oven at the same time and turn it on, and the water will boil before much of that ice even melts. Because the water will receive the energy, it resonates. Those molecules resonate at that frequency, and they will resonate. Their amplitude will shake largely, and but the ice, when it freezes, when the water freezes, the modes of vibration change, and they don't vibrate at the same frequencies, and therefore they just don't accept the energy. So, like for example, if you're cooking frozen vegetables, what they tell you on the instructions in the microwave is to add water. Well, the reason you have to add water to that is because the microwaves will heat up the water, and then that water will start to melt the ice crystals that are in those frozen vegetables, and then the microwaves can then start heating up the frozen vegetables. But if you don't add water to that, it takes a while for the air just to melt enough ice crystals and get that process going. Okay, so our next form is infrared. Okay, unfortunately, some students say it wrong, and they say infrared. Okay, and so night vision, that would be a classic example of the use of infrared heat lamps. For example, you are glowing, you are luminous in the infrared region, okay, because you're warm and you give off light, and that's what infrared cameras do. They receive that information and then they convert it into a visible light that your eyes can see. Okay, so it simply converts it. You can't see in the infrared region, but you can feel heat. You can go to a bonfire and you can say, oh, that bonfire is bright, but all that, you just feel like it burns your skin. Well, that's the infrared. It's not the visible light that's so hot. It's the infrared that's terribly painful if you get too close to a fire. Okay, so your skin is sensitive to the infrared. Your eyes are very sensitive to the visible, which is our next one, visible. So you might be familiar with Roy G. Biv. Okay, red, orange, yellow, green, blue, indigo, and violet. That sequence of colors, that's red is the longer waves, and blue are the higher frequencies, and they are the shorter wavelengths. Those different colors they have different characteristics. The longer wavelengths tend to be scattered less, and so the shorter wavelengths tend to be scattered more. That's why the sky is blue when the light comes in from the sun. It carries all the colors and it scatters the high frequency colors, and that strips off the high frequency, which is the blues, and that gives us the blue sky. The reds, they penetrate more, and they they get scattered less, especially by moisture in the air. And then that's why taillights are red, because they're really important to see. Taillights, emergency lights, we want to make them red. They get broken up less by water vapor. The stop light is red. The go light is green. The reason is it's more important that you see the red one than you see the green one. If you think about a driving on a foggy day and you're on, let's say, a neighborhood near your house, and someplace you go regularly, and you come to a light, and you know there's a light coming up, but you can't see it because the fog is so thick. But you know there's a light, and you're trying to think, well, what color is it? Well, if you can't tell, chances are it's green. And then when you see it go to red, you can see it much better. That red penetrates and is broken up less because it has a longer wavelength. And so that's why they tend to use the red for those things that you need to be able to see. They get broken up less. Okay? So we have the different colors. Then we get to ultraviolet. That has applications with growth of plants. Use a lot of ultraviolet. Sunburns. In fact, you can get a sunburn on a cloudy day. Why is that? Why can you get a sometimes people get really bad sunburns on cloudy days. And the reason is that we often are calibrated. We make decisions about how much sun we've got by how hot we feel. Well, heat, that is the infrared region, but the ultraviolet, that chemical process of burning your skin, that chemical process may take anywhere from a half hour to a couple hours. So there's a big time delay. So a lot of times what you do is you feel how hot do I feel? And you say, I've had enough sun. Well, on a cloudy day, infrared is easily absorbed by water. And so on a cloudy day, as the light passes through the clouds, a lot of the infrared is removed. And so you don't feel as hot. Well, you're still getting pretty much just as much ultraviolet. And therefore, but you don't feel as hot. So you don't take the precautions to protect yourself from that ultraviolet. And so really it's not that a cloudy day, the ultraviolet is worse. It's just that your usual calibration between the ultraviolet and infrared, that relationship is different than what you're used to. And if you're making decisions based on how hot you feel, which is infrared, you will take a whole lot more ultraviolet than you probably think you should have. X-rays. And when it comes to the X-rays, we use those in the dentists, the doctors, for diagnostic purposes. And the reason we use that X-rays is that they penetrate soft tissue, but they don't penetrate bone. And as a result, what you get from that is you can cast a shadow of your bones. If you stand in front of a visible light, regular light, and you put your hand up against near the wall, you'll see your shadow. Okay, and that gives you the basic shape of your hand or your arm or your body. Okay, but if you want to get a shadow of your bones without peeling your skin away, you would use X-rays, and X-rays would go through. They would go through the soft tissue, but they would not go through the bone, and therefore you can cast a shadow of your bone. But you have to have something behind your hand or bones that will detect X-rays. And now X-rays are not good for detecting necessarily cartilage damage, which is soft tissue as well, and it's hard to see that. It doesn't cast the shadow like the bones do. Okay? And then the last one we get is gamma. And gamma are the highest of the energy rays. Now the gamma and the X-rays, sometimes you'll see them referred to as ionizing radiation. Well, what does that mean? Well, that simply means that the light waves or photons, they have higher energy at these high, the gamma and the X-rays, they have high enough energies because they have a high frequency that they can actually dislodge electrons from an atom. And therefore, what you get is an ion, and therefore they're ionizing. These are the ones that are the most dangerous to us because they can cause damage to tissue when they change the molecules because they're ionizing radiation. So you do want to be more careful with what's called ionizing radiation. Okay. All right. Last thing that we want to be able to get to is we want to be able to use our wave equation. So we have V equals F lambda. Okay. So as I said before, main things we want to look at is the relative order of the different parts of the spectrum in terms of frequency, wavelength, and energy. Know which ones have the highest energy, which ones have the lowest energy, which have the highest frequency, which have the highest wavelengths. But we were going to use this equation. Remember that this equation, V equals F lambda, but V is C, which is simply 3 times 10 to the 8th meters per second. You really aren't going to ever use this equation solving for C because we know what it is. It's a constant. You will use the equation in two forms. You will use F equals C over lambda, and you will if you want to find the wavelength, you use C divided by the frequency. And so they're real simple equations. The hardest part is you got to be able to use scientific notation on your calculator. So let's say that we wanted to find out what is the frequency of a wave that's 100 meters long. Well, if the wavelength is 100 meters and the speed of light is 3 times 10 to the 8th meters per second, you simply would take in your calculator 3 times 10 to the 8th, use that EE button on most of the calculators, 3 EE 8, and then divide by 100, and that would give you 3 million, or 3 times 10 to the 6th. And what you would get is the meters would cancel meters. We have reciprocal seconds, and that would simply be hertz. So the frequency of that wave would be 3 million, or 3 times 10 to the 6th hertz. If, for example, you wanted to find the wavelength of some wave that had, let's say, a frequency of 6 times 10 to the 12th hertz, once again, you're still going to use 3 times 10 to the 8th meters per second. But in this case, hertz, reciprocal seconds, cancel those, and we end up with meters. And so we would end up getting, if you take 3 times 10 to the 8th and you divide it by 6 times 10 to the 12th, notice that the denominator is much bigger. You're going to get a wavelength which is really small, and you're going to get a wavelength which is going to be 5 times 10 to the negative 5th meters. Okay, so you should be able to do these two types of calculations, as well as know the relative order of the frequency, wavelength, and energies for the different forms of the spectrum. Now, just keep in mind all the different forms have the same speed. They all use 3 times 10 to the 8th meters per second. So please get that one memorized. That will help you out quite a bit. Okay. Hopefully that will help you.